So now that we've very carefully studied the transformation that we used in the transformation of a rectangle into a cone in the previous example, let's do two other parameterizations of surfaces, and we'll see what we can take from that. The first thing we want to do is we want to give a parameterization of the cylindrical tube described here as a surface in R3. So let's look at the surface first of all in R3. So here we've got X, Y, and Z, and this surface in R3 maybe looks something like this. Well, as best I can draw it. Okay? And so what we want to do is we want to come up with a space U and V that it makes sense to take some region in UV space and morph it based on our transformation or our parameterization into R3. So in this case, I think that our choice, and here I'll go back to calling this R because we so often use a vector valued function in this class at this point. We'll use R as our transformation. I think that we're going to use our R of UV to be these three functions here. One cosine of U, one sine of U, and then we'll let the last component just be V. And I would recommend memorizing this as how you parameterize a cylindrical tube. So notice in this case, unlike the cone from before, this surface always has a constant radius. Remember, this surface is not a solid. It is the surface shell that we've just sketched there. And it always has a constant radius of 1. And so because of that, I don't have a parameter for the radius the way I did when I parameterized a cone. I just have a fixed constant for that radius. And the other thing of note here is that the third coordinate, the z coordinate, is just given by a single parameter. That's like the identity parameter. We'll just let this coordinate be this coordinate. And we do that because z so nicely parameterizes this the surface, because at any point, once we know what x and y are, then we simply just give that height coordinate. So this is sort of a natural choice for what we'd want z to be. So let's go ahead and give our domain and hopefully that clarifies. In this case, u is playing the role of an angle theta here. So u is going between 0 and 2 pi. And in this case, v is simply the same as that z coordinate there. So v is going to go between 0 and the same thing that z went to, which was 3. So if we look at this region, so this region I'm going to call R, folks. This region R, which is the domain of the transformation, if we look at it in UV space, it looks something like this. Let's see here. Here is where U equals 0. Let me do this in green. So here is where U is equal to 0. Here is where U is equal to 2 pi. And then V goes from 0 up to 3. And so this is our region R that is going to get morphed based upon these three coordinate function rules into this solid over here. So one thing I'm going to start doing is we will refer to the domain space that this came from as R, and the space that we're mapping to, the image of that R under the mapping of our parameterization, we'll call it S. And that should make sense here because we use S for surface. So that's that hollow cylindrical tube that we've described there. Okay, so for this next parameterization, what we want to do is we want to parameterize the surface that is this plane in the first octant. So let's just look at our surface for just a moment. We know what this surface looks like. In XYZ space, this would be this surface right here, where up here z is 6, and it looks like x could go out to 3, and y could go out to 2. And so this is our surface in XYZ space. Well, unlike the previous examples that we looked at, first of all, we can solve for z explicitly. We can give the explicit surface as a function of x and y without having to state anything more than that other than the domain. So if I were to solve this for z, I would have z is equal to 6 minus 3y minus 2x. And so we could think of z as a function of x and y. So what's interesting here is I have a nice explicit description of our surface. And this particular surface is best described in the coordinates that I already gave it in terms of. That is, unlike this cylinder right here, which is best described in cylindrical coordinates, or the cone that we did before that, which was best described in some other coordinate system, I think the best way to describe a plane is in the rectangular coordinate system. So when it comes time to pick a parameterization, I'm going to pick what I call the natural parameterization. And this word natural, it's my own word. It's maybe not the best word for it, but I can't think of anything else. Where normally if you wanted to parameterize this surface, you would let R be a mapping from UV space. So let's write it this way. R of UV is equal to, and then you would let U be X, and then you would let V be Y, and then you would let Z be 6 minus 3V minus 2U. But notice that it's almost like I introduced these new coordinates for nothing, because this is the x coordinate, this is the y coordinate, and this was just 6 minus 3x or minus 3y minus 2x, which is how I was already describing the surface to begin with. So if this is the case, rather than giving the parameterization in terms of u and v, or r and theta, we're going to just reuse the same variables that we've already gotten. So what we're going to do here is when we do this natural parameterization, we're just going to say r of xy is equal to xy and then 6 minus 3y minus 2x. And in this case, what I want to point out is that we're doing this because we've got an explicit description of our function here. This is just our f of xy. When you've got an explicit description of the function, and it's best described in the coordinates that it's already described in, then you do one of these natural parameterizations, and there's no reason to introduce new variables into the problem. Okay. So the last thing we have to decide is the domain for this parameterization, and for that, we can determine that by just looking at the projection of the plane into, or excuse me, the actual plane, this plane here, into the xy plane, which is our domain space. So again, when we do this natural parameterization, rather than picking this new space x and y and then think about morphing it into this other space x, y, and z, it's almost redundant to draw an xy coordinate system here. And so what we do instead is we just simply put this xy coordinate system into the picture itself. There's the domain space, and then the rest of it is the 3 space that we're mapping into. And so if we take the projection of this plane down into the xy plane, we would have this picture right here for that space, which is the same as this picture right here, where x ranges between, to be in that plane, x is going to range between 0 and 3, and y is going to range between 0 and 2, but I can't take the that entire rectangle because I need to be inside that triangular region, and so this is described by y is equal to negative 2/3 x plus 6. That should be a plus 2. Okay. So what did I do to figure that out, folks? I said, okay, if we restrict this plane into the xy plane, that would only happen if z were 0, and then I went ahead and solved the resulting equation for y, which is how I would get this description here. So this goes ahead and gives us what we need for our domain, because in this parameterization we're just letting x be x, and the x coordinates in the domain space are going to range between 0 and 3, so we've got 0 less than or equal to x less than or equal to 3. And the y coordinates, we don't say between 0 and 2, we say between 0 and whenever we hit that line. So we've got 0 less than or equal to y less than or equal to negative 2/3 x plus 2. So the point that I'm trying to make by this example here, folks, as opposed to the other two parameterizations that we looked at, is that we simply use what I call this natural parameterization. We let x be x, we let y be y, and then we just restated an explicit description of our surface, and then we simply made sure that the domain worked, with the domain being the projection of the surface into the xy plane, where we think of that xy plane as the domain space, and we don't draw the two sets of pictures like we did up here. When we use uv or r theta or something other than the variables that our surface is currently described in, we need to draw a separate domain space, and we think of morphing the region into that surface. We don't do the same thing when we pick this natural parameterization. Okay, folks, that about wraps us up. The last thing I want to say is, now that we've learned how to do parameterizations, we eventually want to compute various surface integrals, such as, and let me just list a few of these that you're going to see. So we'll want to perform a surface integral. So we're going to integrate over our surface of maybe this one here, 1 ds, or maybe we'll integrate over just some generic function f of x, y ds, or maybe we will go ahead and do some sort of vector operation, like maybe f dot ds over s, or another way of writing that is the surface integral of f dot n ds, which is, this is going to be called a flux integral. So we're going to learn how to do integrals over surfaces, but the starting point for doing that is to come up with a parameterization. But for the remainder of this pre-work, we're simply going to look at computing the surface area through the area finding function f of x, y is just equal to 1. That is, what we're going to be focusing on is computing this surface integral here. And I'm going to have you watch Dr. Bassett do that, derive the formula for it, and that'll complete this pre-work. So finish that up, folks, and then you'll be ready to work through my math lab exercises. Thanks for your attention.